Welcome back to another video of Programming for Data Analytics Part 2. Today we're going to keep talking about machine learning algorithms, and we're going to be focusing on logistic regression or binary classification. Now, if you've been keeping up with this series, we already covered this topic, but we just did the kind of by the book example with the flower iris dataset. What we're going to be doing now is we're going to be doing my own example that I came up with. And we're going to take the other video that we did with linear regression on the cryptocurrency prices, and we're going to take that and we're going to modify that example right now live and make it a classification problem that we're going to then throw logistic regression at to see if we can solve it. So to make sure that we're on the same page, let's go ahead and remember what the difference is between linear and logistic regression. Linear regression is when you're trying to calculate a continuous variable. So for example, with the cryptocurrency, what we said was if we have the opening price and the closing price of Bitcoin, and we look at a different cryptocurrency such as Ethereum, and we feed in the opening price of that, can we predict the closing price based on the other features, which are the opening and closing price of Bitcoin? And we had some success with that. Obviously, it wasn't perfect, but the idea is just to have an example to play with. And so that's a continuous variable because the price of Ethereum is a number. It's a number basically like dollars, and it's essentially going up or down, but it's continuously going. There's no hard ceiling or bottom. Well, I guess zero could be bottom, but I guess, you know, in some worlds, I guess you could go to negative, you go in depth or something. So the idea is you want to be able to predict anything that's ongoing. And it's when we're trying to see whether a model is accurately, predicting this, if it's working, it's not enough to just say whether it predicts the correct amount, because the correct amount might be like $101.25. But our model predicts $101.24, and we're up by 1 penny. So technically it's not correct, but it's really, really close. So we should reward that model versus another one that gets like $50 prediction instead of 101. That model is more mistaken because, it's got a completely different amount. And so we came up with what was mean square error and other different ways of measuring an error for a continuous variable. So that's your linear regression type of algorithms that we covered, and we're going to do more of those later on. But the bread and butter, or like the major sort of interest when it comes to machine learning, I would say is more of the classification problems. The classification problems are more concrete because they're the ones that you're just trying to classify. Given the features that you get for your problem, you're just trying to classify the output into a finite number of classes that you define from the start. In the most basic example, like we're going to be doing today, that could be a binary classification problem. So a yes or a no, a 1 or a 0. So given a bunch of input, you have to make a decision of yes or no. And that's it. That's all it is. In our case, what we're going to be looking at is, because we're going to take the same input that we had before, so the Bitcoin opening and closing price, and then the Ethereum opening price. We're going to take those inputs, we're going to feed it to the algorithm, and the algorithm is going to tell us whether we should buy Ethereum that day or not. And really what it's going to find out is not whether we should buy it, but whether the price is going to be higher or lower than the opening price. So if Ethereum is going to close higher than it opens, so if Ethereum opens at $100 and it closes at $101, we want to get a yes back, because that means it went up. So we should be buying it that day because we're going to make a profit. We should get a no if the price is not going to go up. So basically, if it stays the same, sideways, or if it goes down. So if it, it starts at 100 and it closes it at 99. Now we know that crypto is a 24-hour cycle thing, so closing price is more of just the price at the end of the day. But you can think of that as your closing price because it's the time that you decide what you want to do compared to the opening. Okay, so given this information, it's a simpler problem, at least when it comes to like a decision, because you don't need to compute a moving variable. It's just a yes or no. But it doesn't necessarily mean that it's easier to solve. than like a linear regression problem. It's just you approach it differently. On one end, though, now you have to reevaluate how you want to compute whether something is working or not. So what happens if the algorithm says to buy and in reality it did go up in price, which is ideal, right? So the algorithm said, yes, it's going to go up in price based on this, so you should buy. Obviously, we know the opening and closing price of Bitcoin, so we're kind of cheating ahead, because if we know the closing price of Bitcoin, we would know the closing price of Ethereum. But we're saying in the perfect world where we could see that, but not the other one. In this scenario, we want to know whether the price will go up or down of Ethereum. And so if we get a yes, we buy. If we get a no, we don't buy. So if we get a yes and we buy and it actually went up, that's a win for us. So we call that a true positive, and that's what we want to be the highest, right? We want that to always be accurate, because then we're going to make tons of money or something, right? Now, obviously, there's a difference between it going up by a penny versus $10, because you also have to consider things like trading fees and taxes and all these things, but we're just kind of forgetting about that to make the problem simple. On the other side, the other scenario is that if it goes down in price, we want our algorithm to say to not buy, right? Because it's going to predict that the price is going to go down. In that case, we always want it to say to not buy. We do not want our algorithm to be like overly optimistic and say, buy now, even though the price is going to crash that day, because we would lose money, right? So what that is known as a true negative. So if we get a true negative, it means that the algorithm said don't buy, and we shouldn't have bought because the price did go down. And then, of course, there's the mistakes. So there's things as false positives and false negatives. False positives is when your algorithm says to buy, but the price actually goes down that day. That's bad because it's a mistake. We're buying when we shouldn't have, because that's what the algorithm said. It kind of YOLO'd it. On the other hand, and those are bad because we lose money. On the other hand, we have the false negatives. The false negatives in our scenario are not as bad, because the false negative is saying that our algorithm said don't buy, it's going to go down that day, but it turns out that it actually went up. And technically speaking, if we're not shorting or doing anything crazy, then we won't lose money, because we just didn't buy. We just didn't profit when we could have had. So we're just like, darn it, the algorithm said like not to do something, but we could have done it. So that's in this scenario not as bad. But in some scenarios, it may be very important. So those four sort of different measurements of how good our algorithm is what we're really going to be basing off, rather than just saying how accurate it is. Accuracy, of course, is the decision of whether something, what you got versus what you expected is the same, which does work and does give you a certain degree, and I can show you that. But just like with the linear regression, there's better measurements that give you a better idea. Like if your algorithm is 100% accurate, or actually if your algorithm is 99% accurate, because it always says to buy, and that's just because it happens to be the most of the days Ethereum goes up. But the 1% that it goes down, your algorithm still says to buy. Is it a good algorithm? Accuracy is going to say it's a 99-point-something%, which makes it sound really nice. But if we actually look at these true positive, false positives, which I'll write down later, when we get to actually see what the results are from our algorithm, that's when we would be like, okay, maybe even though our algorithm accuracy is 99%, it's not really working. It's just saying to buy all the time. It just happens to be that the input we gave it is unbalanced. It's mostly just like positive input. So that's just sort of an overview of what we're going to do and how we're going to evaluate it. Okay? So like I said, in the previous videos, I showed you how this works. So I showed you logistic regression with the iris data set. So I kind of expect you to know that. If you haven't seen that yet, you should go see that. Although I am going to show you all of the code, I am going to skip some of that overview because I did that already. And more importantly, I'm expecting you already to see the linear regression crypto video, because we're going to take that code as a starting point and then modify it to create a logistic regression example. So while I'm going to go over the code, in that video, I coded it from scratch. So you really have to see that to go here. But I'm pretty sure most of you have if you're here, because you're looking at the series, right? Okay, so that's it. Let us go ahead and begin. So what I have here is just a copy of the code from that video where we did the linear regression. If I run it, it's still going to see that actually. So you can see this was our estimating our graph from the linear regression, and we can see that we got a mean square error and a mean absolute error of 15. So it's not bad, you know. It's like we're off by $15, which is not bad, particularly if the price is in thousands. Not as good if you're looking at the older prices of Bitcoin where it was like in hundreds, but it's still okay. And we also did some tests where we looked at like prediction of individual moments. So like we looked, I think it was in February when I recorded that video. That we took the time of, February 20 at 5:25 a.m. And this was the opening price of Bitcoin, the closing price of Bitcoin, opening and closing of Ethereum. So we fed it these three values and see how it predicted the closing price. And it turned out that it predicted it okay. Like we were off by $13, but it actually predicted a down of the price. So it actually succeeded in predicting that the price was this was going to go down. But our model was a little bit optimistic because even though it went down, the real closing price was $26.30 and ours predicted $26.44. So it went down, but not as much. But it's still, you know, it still went down by close to $100. Our algorithm is like basically saying, yeah, it's going to go down by about $100. So that's not bad. It would have been bad if it said like, no, it's going to go up, right? So in our scenario now, we're going to switch it. What we want to get from this is a zero or a null, meaning that the price is not going to go up, right? So that's what we're going to do. Now, could we use what we currently have and just sort of make that decision? I suppose we could. We could just, we could take the opening price and then see what the closing prices predicts. And if that number is less than, then we say this is our zero. And if it's greater than, then this is our one. And that would work. So I guess that's one form of classification, but it's not the way to do it. And it's not gonna work out too well for you in a lot of scenarios. So you want to use the right algorithm for, the right tool for the right problem. Okay, so and then we did some graphs and whatnot. So as you saw earlier. So anyways, what I'm going to do is just kind of walk you through the top of the code again, so it refreshes my mind too of what we did, which is just load the data. So we start by loading in the CSVs into a data frame. See, this is why we have comments. Comments are good. You should be using comments because they make you remember code. This code was written basically a month ago now. I don't remember it too well. So documentation helps me remember it as much as it helps somebody else to look at this code and understand it. So it says load CSV into data frame. So that's right. We're opening this Bitcoin CSV and Ethereum CSV files that contain a bunch of columns, more than the ones we use. But we're only picking a couple for this project, which is the opening and closing price. But there's a couple of other values in there, I think. I'm gonna read them in. And then because Ethereum and Bitcoin have existed Bitcoin has existed longer than Ethereum, we wanted to just take a chunk that both existed. So we took the chunk from 2017 to 2021, right? So we basically did a loop that counts how many rows there are that we care about, and then we get rid of the other rows that we don't care about. So that's what we do there. Then we go ahead and drop this SNO column because we don't really need it, because it's kind of like an indexing, if I recall, and it's going to be out of order because we cut off some numbers in between, not in between, but in the beginning of Bitcoin. So we wanted to kind of line them up. So we just throw away a column. So that's what this code does. Like I said, by the way, if you just want to see in detail what everything does here, you can go ahead and refresh your mind by checking out the previous video when I show you this stuff. Then we do the same thing for Ethereum. Very cool. And then we start talking about, I think it's a good idea to always think about what you're going to do and write it down. So you have a clear, goal and game plan of what you want to do in the code before you code it. That way you don't kind of walk yourself into a corner where you just can't get out and you gotta just redo stuff. So we said we want as input the Bitcoin opening and closing and Ethereum open, and as output we want Ethereum closing price. The idea is to see if we can predict the closing price of Ethereum for the day based on how Bitcoin performed the same day and what the starting price of Ethereum was that day. This is to see if there's a correlation between both cryptos, okay? Which we found there is actually, because I mean, we got just with linear regression, we got some decent results. Okay, and then what I'm going to do now is I'm going to create a new data frame that connects both the Bitcoin and the Ethereum one, because I want to line them up so I have all the inputs nicely lined up. So this is when I'm taking the different columns that I want. Well, actually, these are all the columns. So we have the date, price, open, high, low, volume, change, percentage. Obviously, we're not using all of those, but you're more than welcome to try to do something with those and do some logistic regression and then try it out. So you can, try different things than what I show. But ultimately, the ones that we're only caring about are these three, which are the opening, the closing. So the closing price is called just price. So it's just something to be aware of. So Bitcoin opening, Bitcoin close, and Ethereum open. And we're putting that in our X, because, think about Y equals MX plus B kind of thing. So our X is our input features and Y is our output. And so we're putting that in. Now, in this case, because we were doing linear regression, we were storing on as our output in Y the price. But in this case, what we want to store is simply a 0 or a 1. A 1 for when the price goes up and a 0 for when the price goes down. Now, unfortunately, we don't actually have that in here as one of the columns. So we have to make our own. But that's okay, because we can just look at the opening price and the closing price and then compare those two. And if it goes up, then we store a 1. And if it goes down, we store a 0. So let's just go ahead and add some code. And it's a little bit of a good review for our Python programming. All right, so we're going to say new code for logistic regression. So let's make a temporary list. We're just going to call it temporary price, an empty list. And this list is going to store basically stores a 1 for price going up and 0 for price going down. I'm just going to say go down just so that I save some space. Okay, and what I'm going to do is I'm just going to iterate through all of the entries that I have in crypto X and crypto Y that I'm storing, and basically, crypto X actually. I'm just going to iterate through this, which crypto X is just this. So I'm just going to iterate through this list here, and then generate that list. Okay. So basically, for every row in the BTC ETH entry, which represents 1 day of trading, so there's a 1 opening price, 1 closing price for both Ethereum and Bitcoin. For each of those, I'm going to look at those, and I'm going to store a 1 if it goes up, or a 0 if it does not go up. Okay, that's all I'm doing. So I'm going to iterate the number of times that there are rows. So I'm going to get the length of how many rows there are by saying, not length, but the number of rows by using the length variable on this data frame. Okay? If we're curious what this is, by the way, we can see it really quickly. So I can just write an exit so that it stops there. Just so it doesn't do the machine learning every time and run slow. But we can see that that is basically equal to 1697. I believe that's, oh wait, no, I didn't print it. So, although I'm pretty sure that's going to be what it's going to be, but let's just try it. Yep, 1697. So 16, we're basically going to make a list of zeros and ones that is 1,697 entries long. Okay, so that's what we're going to be doing. I'm going to actually keep an exit down here just so that it always stops there while we finish the code. So we can test it, because otherwise every time I run it, it's going to try to do the machine learning model, and it runs pretty quickly, but yeah, it still takes like a second and it slows us down. Okay, so we know this is basically running from 0 to 1,697. And like I said, I'm going to store in temp price. I'm going to append basically a 1 or a 0. That's my goal, to append a 1 or a 0, okay? But I need to choose that based on what happens with the price that day. So I'm going to put an if statement, and I'm going to say if, actually, I don't need the parentheses technically. If BTC So if the price of Ethereum, which is called just price, at that index that we're looking at, so I, because that's the name of the variable for I, if the price of Ethereum that day, which is the closing price, remember price is closing price, if that is greater than the BTC opening price, which is called open, if that's greater than the opening price at that index, then that means that Ethereum went up that day, right? So if, remember, this means closing. So if the closing price of that day, which is that row, so let's say row 5, if the closing price of row 5 is greater than the opening price of row 5, that means Ethereum went up that day, right? Because the closing versus open, right? So if it's opened at $10 and it closed at 20, that means it went up, right? So if it's greater than, this evaluates to true. So I want to append in that scenario a 1 because it went up in price, right? Higher close price went up. This is what we want. You know, unless you want to lose money, I suppose, or you're trying to short the market or something. Otherwise, then it must have gone down, right? So if it did not go, if it's not greater than, and it's either equal or less than. So we're just gonna forget about equal. We're just gonna plus. I mean, why buy something when it's equal in price? Like, I guess, even though we're not really thinking about taxes and trading fees, like, why buy something if it's not gonna go up or down? It's like why? Just don't buy it. So yeah, you're just adding risk. So yeah, so we're gonna append a 0 otherwise, basically, okay? And then again, this is basically lower, or I guess equal close than open. We'll call that the went down, right? I mean, what are the odds that it's actually gonna be exactly the same? It probably won't be. So yeah, put in there for I in range, okay? So yeah, that is all we really need to create this list. But right now it's just a little list. It's just a simple list. So I'm going to convert it into a data frame just to be consistent. I'm going to call that Y2. I could call it Y and replace my current Y that I have here. But I want to keep that in case ever later on I want to combine both like regression in a future video. So we'll just call it Y2. And to convert into data frame, just do PD because it's the Panda import. Call series and then just pass in the list. And then put a false just to optimize. Okay. So yeah, as long as we do this, we have created it. So let's go ahead and print it out just so you can see it. Print out crypto Y2, and like I said, just terminate there so it doesn't run the rest. So we can see here that we have 1,697 rows, and it's just made up of a bunch of zeros and ones. As you can, this is just a row number, and then this is the value. So we got 1, 1, 1, 1, 0. What this means is that the first 4 entries there that we have, the price went up. And then the 5th day, the price went down. And then the last entries that we have, we can see the price went down this day, and then it went up these 3 days. So you can see that fluctuation, by the way. That's volatile. So yeah, and if you don't believe me that this is working, let's just really quickly, show those entries on BTC ETH. So let's just say like print BTC ETH. How do I print the full row? It's gonna oh, here, dot values at 1696. Keyboard's kind of slowly dying. I have a new one already. I have to plug it in, but sometimes it doesn't type something. So let's just print out the last 4 days, so we can see if it really went up. Well, that's 5 because I can see it. It went up, down, and then up, up, up. So this is gonna be 95, 94. See, the keyboard doing more. 4, 3, 2. Okay. So what I'm doing, by the way, is when you do data frame, if you put values, I think it'll get the values, and then it'll actually print out the index. There we go. Because otherwise, if I do this instead, it's actually trying to find a row that's called 1692. So like when you're just trying to get a specific row, you pass that in to like a key. Remember, you're hashing. like remember hashing it and how you pass that in. It's kind of like that. And then you pass the index that you want. So like, I want row ETH price, or sorry, column, I said row. You want column ETH price, and then you want the row 20 of that. So that's how this usually works. But if you just want the entire row of something, then you just convert this into values. That'll convert the current the current data frame into just the entire row will just be like a list, and then you can just get the index of that. So that's why I put the word values here. Just want to make sure you're on the same page. Okay, so we can see the prices. So like, I don't really remember the order of these things though. Darn it. Let's see what it is. Column. So we got date, price. So open. So we got the closing price and then the opening price. And then, so let's see. So this is date, closing price of Bitcoin, opening price of Bitcoin, the high, the low, the volume, the change. Okay, so if we go further, oh yeah, we got rid of date. That's why. I was like, where's date? Okay, so I think these two are the ones we care about. All right, so we got 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6, 7. Yep. Okay, so this one's the closing price, and this is the opening price. Okay. Let me scroll that up so you can see that. So I know I'm blocking it a little bit. There we go. Closing price and opening price. So you can see that if this is the opening price and this is the closing price, it went up this day. Okay. So remember, what we're looking for is the 1011, right? That's what we stored. That's what we said, that like the last 5 days of this list goes up one day, goes down another day, and then 3 days of up. So yes, this matches. This goes up this day, and then the next day it should go down. You can see that it looks like I want. I skipped the line. I was like freaking out. Here we go. This is the next one. So you can see that the opening price was 3,285 and the closing price was 3,223. So that is right. So they will go down on August 21st, 2021. So, yep. So that means it did go down on the day after that, which matches ours. And then the last 3 days, it should be just up, up, and up. So, yep, this goes up a little bit, but it goes up. This one goes up also, well, that's not a little bit. This one went from 3,200 to 3,300. And then this one barely went up from 3,322 to 3,329. So, like $7. But still it went up, okay? So hopefully that proves to you that this is indeed working and that this list matches whether it's going up or down in price, okay? So, I don't have to prove to you, you should trust me, but at the same time, you should be doing this kind of things to verify that you didn't screw up, because you want to know this early. You don't want to like think, oh, it's working, and then not, do the code, and then you're freaking out why it's not working. Not like predicting correctly, and it's because you screwed up the input for it. So of course it's not going to predict the right thing. Okay. So yeah. Okay. So anyways, we're good to go on this. We have this, which is our output, and then we have our input, which is the crypto X, which is those 3 features. And obviously, if we cheated, I don't know if you consider cheating it, but like if we actually gave it the closing price, the model should like be smart enough to predict. We can actually do that later. That might be interesting to see, because like if we give it the closing price, like the model should like be like actually the AI will be like, yo, I found a pattern that like whenever the closing price is higher than the opening price, I just get a 1 the whole time. So it'll actually detect that, and it'll actually give you really high accuracy. That shows you that the AI is not like completely dumb per se, or in this case, the model is like working. But in this case, it's not giving it the whole story, because like, as we saw, not all the time is there a connection, like not every single day between Bitcoin and Ethereum. Some days it kind of goes away from that. But the trend seems to be like they're correlated, at least for the times that are here. So yeah, so that would be a nice little thing to try out. And if I don't try it, if I forget by the end of this video, you should try it out. And your accuracy should be really high if you add that, because you're pretty much giving it the answer, just not telling it that it's the answer. You know, you're just kind of hinting it, I guess. Okay, so we have our Y2. So we can kind of keep going with the code that we had before. So remember, the next thing we did was we split the data set into training and testing, right? So when it comes to like classification, so like if you saw the last video with the iris data set, like I just kind of fed it the whole data set and just see how it worked. You could do that, but I still am of the idea that you want to have a testing and then you want a training set. Sorry, I mean, you want to have a training set and then a testing set and even a validation set later on, because it makes sure that you are not overfitting to your data or underfitting, and it also makes sure that what you actually achieved is genuine and it's going to not just work for your specific scenario, but it's going to actually be able to be used in the future data that comes in or other scenarios. So that's why we're going to stick with the whole splitting thing again into making 80% training and 20% test. If we're doing validation, I will do something like 70, 20, 10, for that. But yeah, we're keeping this random state stuff because remember, there is this, when you're trying to converge these algorithms, you got to start somewhere in that, U shape. And so if you start in different places, you can converge differently and get different outputs each time. You might just get really lucky and get really good output ones. And then, you might think that, oh, your algorithm just works the whole time, but you just got really lucky. So if you at least want to prove that you got really lucky, you give it what the original seed was, so that at least they don't think you're lying. You're like, hey, no, it just happened. So that's why I like to give a random state. It's also that way consistent, and you can tweak other things and see if it removes one less factor that is affecting it, so you can have more control over your code. The only thing is, instead of feeding it the crypto Y, which was the closing price, I'm going to feed it my list that I just created, whether it's with 1 or 0. So I'm going to put a 2 in there, and that's all I'm going to do for that. I'll write a comment that I did that though. But new modified Y to Y2 for log regression. Okay. So now we are ready to actually create the model. So we're currently using a linear regression model. So now we're going to be changing that to use a logistic regression model. So all we got to do is just change the import. So from scikit-learn import linear model, we could leave that in there. But what we want to change here is, instead of this saying linear regression, we can say logistic regression. Okay, and that should work. Let me just exit here just to see if I don't get an error message from that. Yep, okay. So yeah, I just want to make sure I remembered it. So that's, you can see how nice this is. Like, you don't need to remember magic to be able to get stuff like this working. With scikit-learn, whether you choose to use this model or like this, like if you want to use linear regression, logistic regression, decision trees, support vector machines, random forests, neural networks, whatever model, machine learning model you want to use, it's just as easy as calling the name of it, and then voila. So like, and in the future video, I'm going to in the future video, I'm going to show you like other models like support vector machines, and we can revisit this example just because you can see how quickly I can do it. Like, I'm just literally just going to change this line, and maybe the fit, I could tweak that if I want to tweak any of the custom parameters, which I don't have to, and then bam, I'm running a completely different machine learning model. So like, this is really like, if you get this one going and you get the linear one going, you're set. Now it's just a matter of trying different models, and you can just really have the full power of machine learning in your hands. So yeah, that's why I like scikit-learn. It's very nice about that. Okay, so yeah, as you saw, I'm changing that from linear to logistic, and I'm good to go on that. Next, I want to do the, actually, I'm going to add one more thing to, yeah, so instead of calling this reg, just so I don't get confused later on, I'm going to make it called log reg. And I know I'm going to have to replace it in every single line, but that way I don't accidentally run. I want to make sure I want to check each of these as I enter them. Okay, so I changed the name, variable name intentionally just to make sure things work. I'm also going to pass some parameters to the logistic regression model. I want to pass that random state again because of what I said. So the model always gives me the same outputs. And then I'm going to, if you remember the other video with the flowers, we had a solver in there. And I explained a little bit about how the solvers work so you can check those out. But yeah, I'm just going to throw in a solver, and I'm also going to throw a limit of how many iterations before it should converge or just stop. So yeah, I'll throw those in now. We can try running it without this and see if we get the same result. But yeah, and how do you know what arguments to use for this stuff? You can go with the default, but obviously if you want to get the the best bang for your buck per se, squeeze all the juice out of them that you can get from this, is you want to go look at the documentation in scikit-learn's website for each of the models, and then see all of the arguments and start tweaking with them. Like what, things like you can change in there that are more meant for your type of data. So if you recall, if you're doing binary classification versus multi-class classification, so here we just have a yes or no answer, but imagine that we had like a 1, 2, 3 answers, right? One of them is like a strong buy, a weak buy, a don't buy, and for that way we need to like decide what a weak buy is. So maybe like the price increase is higher than 10%. That's a strong buy. A weak buy is that the price increase is between 1 and 10%. And then a don't buy is that the price is 0 or negative. In that case, we have multi-class classification, right? So we can use a different solver for that that's more optimized for that, because it can converge quicker and be done faster, or one that it maybe gives you a better result but takes a longer time to run. So that's what the solver did. Like I said, check that video out. And I also have links there for documentation for the solver in that video. So for now, we're just going to use that one and go with it. Maybe we can tweak with that once we finish and see if we can improve. Because I think that's the one that I used for the last one, right? Yeah, LBFGS. I mean, here let's very quickly go to the log regression. scikit-learn and look at the solvers actually. So let's see, solvers for small data sets. Linear is a good choice. Handle multi-class. So maybe we should be doing linear. The default is LBFGS, so we'll leave the default like that. So yeah, we'll leave it like that. It means if I didn't put that, it would have still used this one, but now I'm being explicit. So we'll leave that there, and then maybe we'll try one of these once we get going. Okay? So anyways, now that we did that, it comes time to train the model. So like I said, I changed this intentionally so that I can manually add it in each one. So I want to make sure I don't crash by not tweaking each of these lines or reviewing them manually, okay? So for example, here, I am going to keep the same thing with the train and the Y train. I might have to put the word values in here, like this, but I'm going to leave it like that for now. Unless I get this warning that I think I'm going to get, I'll let it be, okay? So that's fine now. Doing the predictions is the same way. So yeah, I just got to update that variable name. Like I said, I didn't have to. I could have left the same variable name and not do these changes. But I want to do that because I want to make sure that I kind of like review each step and make sure that it's still like okay. It's like forcing me to look at them. Okay, it's forcing me to look at them and make sure that they're okay. It's completely unnecessary, but I don't know. A lot of things are unnecessary, but you do them because you want to be careful, right? Cautious. But yeah, that's it. Yeah, this will train it. The fit will train it, and then we can test it using the prediction. So yeah, that's good to go. As you can see, we tested with the testing data set, But we could test it also with the training data set to see how accurate it got. So yeah, we are going to change the metrics, because like I said, we don't want to use any of these mean absolute value stuff anymore. So I'm going to go ahead and delete all of this stuff. We're going to leave the sample test section because I do want to run the sample test. Yeah, we'll leave it like that. Okay. I want to print out to see if it works. So let's go ahead and print out prediction, and let's print out test. So what is test and what's prediction? So remember, this is the is it called the y test? It is called y test, yeah. So fit is actually like training the model. Prediction is you're feeding it the testing data set section. It's trying to run each of those one at a time and then storing the output here, which is like the one or no's. So this should be a list of one or no's, one or zeros. And so I want to print out that list, and I want to print out y test. The y test is the correct answer. That's the one that we actually did with the loop. So in the perfect world, both of them are the same, and that means like our model works every single time. But it's more than likely not going to be the case. But still, let's go ahead and run it and print out just to see if it's at least working. You can see that it runs pretty quickly. I'm glad. It's a small data set. We're only feeding it like 1,600 lines, well, 1,700 almost. But even then, it could take a while if it was like a lot of data in that line. But it's just basically 3 features that we're feeding it in, right? Opening and closing price of Bitcoin and opening price of Ethereum. Those are the 3 features we're feeding it. And then we have the output, which is a binary class. So, but we could try tweaking the solver and see what happens. But anyways, we can see here, this is the, I presume that this one here is the prediction one. And then this one here is the test one. So I guess the prediction one, we got us a normal list and not a data frame. I can already see a mistake though. So you can see that in the beginning, the predicted was 0, 1, 1, 0, right? So that means that the algorithm predicted that day 1, it goes down, day 2 and day 3 goes up, and day 4 goes down. You can see here that in the beginning, it said it goes down. So the first day it nailed it. The second day it nailed it because it said it went up. But the third day it said it was going to go down, whereas it actually went up. So I guess that's not too bad. Remember that was a scenario where like it's saying it's going to go down, so don't buy, and it actually went up. So at least you didn't lose money per se. But the one after that, it says to buy. So the fourth day it says to buy when actually it's going to go down in price. So that's bad because it says to buy, but the price actually went down, right? Or sorry, no, I'm flipping it. My bad. So because this is the one that's predicting. So actually it's saying buy and buy. So it says don't buy and then buy. But the third day, it actually went down in price. So the third day is bad because the third day we bought because it said that the price was going to go up when it didn't go up, okay? So you can see there's errors there. And then let's look at the end. So in the end, we have buy and then 3 days of no. Here, it's just like the correct answer was every single day it went down. So we would have lost money at least if we bought this day. But at least the other days, it understood that the price was going down. So that's okay. So you can see there's some errors, right? But I mean, trying to kind of compare, you know, like look at both of them and see how good it did like that way isn't really going to get us anywhere. So what we want to do is we want to do the metrics, right? We want to compute those metrics to see how it did, you know, from a mathematical perspective, in terms of accuracy and this true positive, false positive, true negative, and false negative scenarios. Okay? So before I go any further, let's talk about those. Okay? So when you're trying to write down the 4 different types that you can have here, and I'll leave a link in the description below because there is a scikit-learn. There's 2 scikit-learn links that I want to show you when it comes to this metric systems that they use for classification. But anyways, I'm going to kind of go with mine for now. The reason why is because so I'm going to write the 4 scenarios here, but I was trying to see if I could match the order that they do them on the documentation. So I think they do like this. Okay, but it doesn't really matter when you're drawing it how they do it. It's just like, flip the box. But yeah, so you have the 4 scenarios. You have true negatives. So let me just write them down, what they stand for. So we got a true negative. We have a false positive. We have a false negative. And we have a true positive. I know when I think of them, I usually put true positive and false positive first, and then put the negatives because just how I like it organized. But I don't know. It doesn't really matter. But let's make sure we understand them, okay? So let's look first at true positive. This is a good one. In fact, we have 2 of these that are good. 2 of these are good and 2 of them are bad per se. So let's actually highlight both of the good ones. The ones that say true, the keyword true is what we want. That means that we got the right answer, whether that be a yes or a no, a 1 or a 0, okay? So a true positive, again, is going to be when the algorithm said yes, and the correct answer was yes. So the price is going to go up, and yes, the price did go up. That's a true positive. A true negative is when the algorithm said no, the price is going to go down, so 0, and the price did go down, okay? So ideally, in the best case, in the best world scenario, you have only true positives and true negatives, and you have none of the falses. Of course, life is not, the machine learning is not that easy that you can just nail this on the first try. That's okay. If we did, then we will have Skynet taking over or something. But we also have mistakes, and we have 2 kinds of mistakes. We have the mistakes where the correct answer is the price is going to go down, but we still said yes, which is a false positive. To kind of understand why this means that, is just think about the word false and positive. So positive is yeah, go buy it. Yes, 1. I'm being false about that. I'm lying. I'm fake. It's like a fake positive. It's like, think about imagine that you get a test for a disease, and it gets a positive test back, which we know positive means you have the disease, and it's a false test. That's bad, right? Because you're going to freak out. You're going to be like, yeah, you have this disease. And you're like, oh my gosh. And then it turns out, nah, just kidding. And you're like, oh my gosh, that's messed up. So yeah, that is a false positive, okay? Those are bad. In the case of a disease, it's really bad because you freak out, right? But at the end of the day, it's bad, but okay, other than you're emotionally damaged from freaking out. Imagine you take a COVID test and it says you have COVID. You're like, oh my gosh, I have COVID. But then you go take a second test and it's like, no, you're okay. It was a false positive. Sure, you're freaked out, but at least you don't actually have COVID, right? The other scenario is bad because imagine you take a test and the test is like, nah, fam, you're good, no COVID found. And it turns out that you actually did have COVID. And now you're walking around super spreading it or something, right? Creating the next wave of the pandemic. Or with the STD. Imagine you have an STD, or imagine you take a test and it says, no, you don't have the STD, but it turns out that you actually do. And then you don't get treated for it. So then it becomes a problem, right? So from a medical point of view, I would say that you really don't want to have false negatives, but false positives is something that you can live with. So probably, when you're trying to do something like a COVID test or a disease test or something like that, for a medical point of view, obviously you don't want either of those. You prefer a perfect world to have true negatives and true positives. But if you're going to have some error, you probably want to have the least amount of false negatives, and then false positives you can live with because you can retest, right? You can retest to make sure if you get a false positive. So a lot of the times when you test for something like disease, even COVID, they say get a second test to confirm. If you got an antigen test, do a PCR test, just to make sure. And that's okay, it kind of ends there. But false negative is really bad because you might be under the false pretense that you're okay when you're not, right? That's from the medical point of view. For us, how does that affect us? Okay, so for us, a false positive is basically saying buy when you shouldn't buy, which makes us lose money, right? So not really good. We don't want that. On the other side, the false negative is not too bad for us. A false negative is basically saying our algorithm said don't buy, the price is going to go down, but it actually went up. So you lose profit because you could have like bought the stock and made money, or bought the crypto and made money, but you didn't. So you're like, oh well, like shrug. I guess maybe next time we'll get it. So there's no major loss, right? So in this scenario, the false negative is not too bad. Like you can have a bunch of false negatives. Like I'm okay if my algorithm is super conservative, right? Because that's really what it means. So if an algorithm like that, it has a lot of like false negatives and not a lot of, and like no false positives, that's like a conservative algorithm. It's basically saying like it's always going to say no, and only when it's really, really sure of a yes, then it'll give you a yes. Okay, that works for stocks because like you want to make sure you only buy when like the price is for sure going to go up, so you don't lose money. So in that scenario, we want to look at the false positives as like, well, we want to decrease that as much as possible, and then the false negatives, if we got a bunch of errors in those, like if we decrease those at the cost of getting more false positives, then we don't want to do that, right? So you can see the big difference. For finance stuff, like false negatives or like whatever, false positives are a big no-no, which is the complete opposite of the medical one, right? Because in the medical one, like you don't care too much about false positives. You obviously don't want to get too many because otherwise your test is just like, yeah, everybody has COVID. You have COVID, everybody has COVID, right? You don't want that. But at the same time, you are willing to accept false positives as long as you keep the false negatives low, because what you really don't want is a test to just say you don't have something when you do, because that becomes a threat, because like that person is actually sick and they can spread it, right? Or if it has like, again, like some STD or some cancer, and then they don't get treated because they think they don't have it, and then that's really bad, right? So you can see how in different domains the error type matters. For the medical domain, we want to give a high weight to not getting false negatives, and false positives we can kind of live with. We obviously don't want them to be too high, but like, we're not too concerned. For the finance domain, it's the complete opposite. We definitely don't want false positives, false negatives. Like, yeah, okay, whatever. We can call it a conservative algorithm because it's only going to buy when it's sure. Okay? So, yeah, and that's why we're splitting the errors like this, because accuracy, if I just tell you the accuracy of my COVID test and the accuracy of my finance model, like, that doesn't tell you anything about that, right? Like, I could have a 90% accuracy finance model where it just has a ton of false positives, which really sucks. Or I could have one that has like an 85% accuracy, but guess what? It has no false positives, only false negatives, which means you're like it's gonna be clean. It's only gonna buy when you're for sure gonna make money, right? And of course, I want to keep that 85 one, even though the accuracy is lower. On the other side, with the medical one, you could have a COVID test that is like 99.9% accurate, but guess what? All the errors it gets are false negatives, and then you're like, ooh, snap. So, like, that means that there's going to be a lot of people that potentially, don't get flagged as being sick. Not so good. I'd rather have one that is 95% accurate, but there's no false negatives. So, like, if somebody has COVID, for sure it's going to pick it up. Obviously, I'm talking ideal world. Most likely, there will be some false positives and false negatives, but again, we're trying to kind of decrease them so that we keep a low amount of the error that we don't want. And so on, and there, a lot is I would say most of the time they are like this. Like you raise one and the other one goes down. But in some cases, they all just kind of go up and down. Like you can just really screw up the algorithm and everything just goes up. So, okay. So this is important metric to understand, and I hope that I kind of made, my case as to why you have to analyze your problem that you're working with and see which kind of error you want to decrease once you figure out what that is. And how we're going to see it is we're going to basically make a list of all of the outputs that we have. So, and then we're going to fit them into this category, and then we can make it into a percentage or just a number of each, and so on. From there are other metrics that combine these, okay? So I don't need to show you what accuracy is, because accuracy is just taking the correct ones and the incorrect ones and just getting the percentage of that. Basically, if you're trying to compute the accuracy of something, I suppose that would be is the true negatives plus the true positives over all of them, which is the true negatives, the true positives, false positives, and false negatives, right? Because that covers all of them. So that's, I guess, your accuracy, right? So like, for example, let's say you have 10 values that you're testing, right? And of those 10, let's say that 7 of them are true negative and 1 of them is a true positive, and then you have maybe a 1 false positive and 1 false negative, right? So what that's saying is that 8 out of 10 are the ones that you basically got right. So that would give you a 80% accuracy, right? But again, that doesn't really tell you much about the type of error, which is why it's nice to see accuracy, but it's not enough. It's not enough to really understand if something is good or bad, okay? So we have accuracy. We also have 2 other metrics that I want to talk about that make use of these 4 different values, and those are precision and recall. So what is precision? Let me write the formula first and then kind of explain what it really is. So it's going to take the true positives and is going to divide it by the total of the true positives plus the false positives, okay? So when you're trying to compute the precision of your model, and by the way, this is going to work for binary classification. When you do multi-class, it gets a little finicky. I'll leave a link in the description below for that, but right now we're just focusing on binary, because otherwise, like, you can see how, like, this is for yes or no's, but like, if you have class 1s, 2, and 3, then there's like false positives. It gets kind of messy to define. So yeah, we're just kind of brush that to the side. But yeah, so when it comes to a precision, what precision is telling you is like, of the number of times that your algorithm gets it right to like buy something, so like true, positive, like what percentage of that is it also giving you like a fake buy? So like the total number of times your algorithm is like buy, like how optimistic is your algorithm really versus like how realistic it is. So in other words, if you want an algorithm that that works for finance, we want something with high precision, right? Because what's going to punish your precision? Like, what's going to make your precision go down? In this case, what's going to make your precision go down is when you have a lot of false positives, right? Because you can see that, like, if you have 0 false positives, then you're just dividing the same number by the same number, right? So like 55 by 55 is 1. 0 and 0, well, no, it's not 0 and 0, but like 20 and 20 is just 1, right? So if you have no false positives, you're just going to get a 1 out of this. And that's, you just think of that as a percentage, so 1 is 100%, right? What's going to make that precision go down is when you have false positives. So if what you're interested in is an algorithm that does not have false positives in it, you want the highest precision algorithm out there, okay? So if you're looking at 2 algorithm outputs, and one of them has a 80% precision and one that has a 90% precision, You go with 90% precision because you know that it's going to have less false positives overall. What precision doesn't tell you is anything to do with false negatives, which in our finance case, we don't care about. We're like, yeah, I mean, well, we do, but like, we don't care about it as much. So like, we don't really need it for this metric of like figuring out whether the algorithm is going to give us false negatives or not, because you're like, whatever, you know, if we don't buy one of the days that we should have bought, okay, whatever. As long as we're only buying when we should be buying and not losing money, that's what we want. Of course, precision is going to be useless for the medical one, right? Because like the medical one, we actually want to give a lot of weight to these false negatives. So it's not really going to serve us well for that. So for that, we can look at the recall. So let's put the recall one. So actually, well, here, let me end this by saying this is basically sensitive to false positives. You know, the less the better. Maybe like good for finance, bad for COVID test, which you get that's going to confuse people. Let's just say bad for medical. Okay, so that's precision. Recall, let's go ahead and put that formula. It's going to be, again, the true positives on the top, which is like all the good stuff you hit. By the way, do note something about precision, by the way. There's also no look at the true negatives. So you're not rewarding your algorithm for not buying when it shouldn't buy. So like if your algorithm is not buying when the price goes down, you're not really caring about that. I mean, you should, but precision won't tell you about it. So just keep that in mind actually as well. So recall is going to be true positives over true positives, but in this case, instead of adding the false positives, we're adding the false negatives. Okay? So this is kind of like the inverse. So this one is going to be sensitive to false negatives. Okay? This is the good one for the medical people, not so good for the finance. So I guess I'll write that here. Sensitive to false negatives. Okay? And I guess, yeah. Let me just write it all. I don't need to write the word, you know, the less the better, but I'll just write good for medical, and bad for finance. Right? So like basically the opposite. So basically, the more false negatives you get, the lower the percentage is going to be for recall. So if you want 100% recall, you have no false negatives in your algorithms, which is good because it means your like medical test never tells you that you don't have the disease when you actually have it. On the other hand, if you have a bunch of false positives, so basically like you want to know a way that you can just always have 100% recall. Just like literally have your test literally say yes every single time. Just hard coded to say yes. It's like if you ask me if you have COVID, I'll be like, yep, you have COVID. Do I have COVID? Yep, you have COVID. Is your algorithm good? Not really, because it's just literally saying everybody has COVID. But your recall is 100%. So you can see that like it's not enough to just look at these two metrics, but there's in combination they can be useful. Because now the precision is going to be 0%, right? Because if it always says yes, well, not 0%, but it's going to not be really high because they have a bunch of false positives in there. So the combination of both of these kind of give you a better idea of what your algorithm is good at. Is it good at is it not good at, but what is your algorithm not so good at? Is it not so good at picking up false positives, or is it not so good at picking up false negatives? In the ideal world, both of these are 100% if you have no false positives and no false negatives, or they're going to be really close to 100% if you don't have one of the two errors. So it's not enough to just look at these two. You still want to look at all four, but it's nice to have two numbers to compare in their cleaner to better understand like which algorithm is better for your usage. Okay, so the last thing is the harmonic mean. That's also nice to know, but that one I'll just I'll show you in the code. So yeah, so now you understand this in detail and what you know to put more care depending on your application than another to this metric than the other ones. Let's actually look at the metrics to see how hard it is. Because I mean, like, the model worked, it ran, but we haven't even seen the accuracy or anything so far. So let's go ahead and do that. So the first sort of metric that I want to show you, kind of just to quickly do, is score metric. So we have technically two scores that we can look at. We have the one from the training and then one from the actual testing data sets. So let's go ahead and look at both. Let's see if like the accuracy or the precision or whatever is going to be lower for the training set than the test set or otherwise. I mean, in theory, they should be about the same if our algorithm is doing a good job. If it's overfitting, then the training would be really high and then the test would be really low. If we have the other way around, then that's some spooky stuff. Like if our training data is not working really well, but like our test data is just magically working, that just means your test data is messed up. Like you probably have like one class, or you just like, some weird luck that you got into. So yeah, test score and train score. For the test one, I am going to feed it test. Actually, this one feeds it for the entire data set, not just the train or the test. So this one should be actually X train. Nope. Y train. And this is X test and Y test. Okay, we run it and nothing happens because we don't print those values out, but let's go ahead and print them out. So what the score one is doing is it's actually giving you accuracy, but it's a little fancier than just doing accuracy by hand when you're doing a multi-class classification. So for now, just think of it like just being accuracy. So let's print both of these: accuracy for train, accuracy for test. Okay, let's do one more. Overall score. For that one, let's go ahead and just do the entire data set. Okay. All right, so let's run it, and we can see that our training accuracy and our testing accuracy are really, really close, actually. That's good. That means that we didn't overfit or underfit. Well, underfit maybe, but definitely did not overfit. And then our overall accuracy, because both these are really close, then of course the overall accuracy is like around the same. But yeah, I mean, we only got 77%. So this isn't like an amazing algorithm output. This is like, I mean, we haven't looked at the true positives and false positives and all of that. We'll do that in a second. But just from the accuracy itself, it's kind of like saying, like, 3 out of 4 times our algorithm works. And then that 1/4 time we lose all our money probably. So I wouldn't bet my life savings on this algorithm. But it definitely, it's cool. I mean, it's better than 50-50. So I guess it's better than flipping a coin. So there's that. But yeah, okay. So very cool. That's just accuracy. Let's go ahead and actually start looking at the precision recall and all the true positives and all that, because that's really going to tell us like how this is doing. So let's go ahead and just do that for the test data set, because that's really what I care about. Like predict the training one, like whatever. But the test one's the one that like the algorithm hasn't seen it. It didn't train with it. So that's the one that I'm gonna know what's up. So let's do it. By the way, just to make sure that this is working, let me make sure that it's like actually doing all of the inputs for the overall one. So let's do like length of y predict, which is what we fed it, right? Because do we ever like? Yeah. Because this is y test, so yeah. 340. Okay, so the size of the test data set is 340 entries, which makes sense because that's about 20% of the 1700 entries that we have, right? 17 times 4. Sorry, I'm kind of right. Okay, cool. All right, so let's go ahead and do metrics. Yeah, let's do metrics. So metrics, precision recall. Let's just do precision recall, S-score. Yeah, this is the S-score one. And so we're going to pass in our test, which is what the correct answer is, and our prediction, which is what the algorithm gave us. And then for now, let's just leave it like that. I'm going to add labels later, but yeah, if we run it like that. Oh, and then let's print it out so we can see it. There we go. So you see this doesn't look pretty at all. It's just kind of like it says array, and it just got some data in it. But this is actually the precision and the recall. So this one's, if I recall, this is precision, this is recall, and then this is harmonic mean, and then this is how many of each class there are. So what I mean by that is that there's 173 of probably class 0, so there's 173 like instances of no, and 167 instances of yes. The reason you want to see if these are like equal-ish is because then you know that your test data set is like balanced out. Otherwise, you know, you might not be testing thoroughly the scenario. Like if you just feed it like 90% yes and 10% no, it might bias your like metrics because you're not really measuring how good it's doing in both scenarios, that, you know, with positive examples and negative examples. So what does this tell us? If this is precision and this is recall, remember, with precision, it means that there's, you know, it lowers our precision if there's false positives. So this is telling us that because the recall is higher, it's telling us that there's more false positives in our code, or sorry, in our model, than there is false negatives. So I suppose that's good for the if this was a medical like model, but for us with the finance one, it's not too good to have to be in that scenario, right? Because we actually would have preferred to have a higher precision, which means that there's less false positives, less times that we actually buy when we shouldn't have, and then the recall, like, it's not, you know, whatever. If it's low, it's low, because it's just saying, you know, we're not buying when we should. But this is, I guess, you know, what this really tells me is that we're buying a lot of the times that we should, so we're not missing out, and then we're having a lot of false positives. So it feels like overall our algorithm is very optimistic. It's like saying like, YOLO it to the moon, buy. That's what I'm getting a sense from this. That's the kind of sense I'm getting from the model, that it's overly optimistic model, I think, just from looking at that. But let's actually compute these by hand to make sure that I'm not flipping precision and recall, okay? And also because it's good practice. But before I do that, let me show you this label variable that you can put. So with the metrics, with this precision and recall function, you can actually pass something known as labels, because you might be asking like, okay, if this is precision, if this is recall, and this is harmonic mean, like what does this first number mean? Like what are these? Well, it's kind of weird. It makes more sense when you're thinking of like multi-class classification, But what it's doing is it's like we make the assumption that a false positive is a one where we get a 1 when we should have gotten a 0, right? Because we're thinking of the 1 as a positive and the 0 as a negative. So in that scenario, a false positive is that. But what if we wanted to make it the other way around? What if we wanted to think of 0 as the positive case and 1 as a negative case? If we did that, and if we computed our precision and recall that way, then we would get these numbers. So that's how we're getting these numbers. So it's kind of trippy, like why you would do that. It doesn't make much sense in binary classification because it's very clear to say what yes means and what no is. Like yes means yes and no means no. But it's a lot easier to understand this when you're looking at multi-class classification. So if you just want to see for one class, you can just pass that label and say like label 1. Oh, sorry. The labels have to be passed as a list. So, like that. Okay, so you can see now that we're only getting what we intended. So like 1 is considered the positive, which is like what we normally assume, right? Like we don't think of 0 as positive, like because Boolean algebra, right? 1 is true and 0 is false. So yeah, we can see that, and we can see that it counts how many of those we get, and if we do 0, we would get the other ones. So that's a scenario where we think of 0 as positive, which is weird and it kind of flips my brain upside down. But you are able to do that if you can, if you want. Don't let your memes be dreams. Or you could just print them out both, like that. And just remember that the order of the labels is typically going to be 0, 1. But if you want to be explicit, you can do it this way, just so there's no confusion. So I'm going to actually leave that in like that. Okay. So I am getting 2 warnings. Oh, it's from the bottom of the code. That's fine. From whatever's on there. It's okay. Yeah, okay. So like I said, let's go ahead and compute our precision and recall by hand. But to do that, let's actually figure, like, we still haven't seen the number of true positives, true negatives, false positive, and false negatives. So how do we get those? Well, we have a function for that, and that's the confusion matrix, because the name of this little square here is the confusion matrix. Now, confusion matrix means a lot of things in computer science. There's another definition when you're talking about like NLP. So we're strictly talking about with machine learning, confusion matrix is going to be this little like 2 by 2 square that contains the true negatives, false positives, false negatives, and true positives. Okay? So now that we've sort of established that, let's go ahead and get that. So let's just say metrics dot confusion matrix, and then just pass in again y test and y predict. And again, we're only looking at these for the test data set. Okay, if we could look at that for the overall and whatnot, but I'm just focusing on the test data set. Okay, so the only thing is that actually not here. Let's just print it out. Yeah, let's just print that so you can see. So here you go. This is actually the output of the confusion matrix. Now it's not very clean, as you can see. It's just a little list. It's a 2D list technically because it's 2 rows, but it represents that matrix. So this is where the problem comes. Like which is which, right? Like I want to make sure that that this matches that, right? Because I have on the top left corner I have true negatives. Is that what this is? Is this true negatives? So I think so. I think that's the one. I think that's how it's set up. But if you actually want to check, that's when you would look at the documentation. And it turns out that that is the case. That the top left is true negatives, and then the top right is a false positive, and the bottom left is false negatives, and the bottom right is true positives. And that's just the way it is. So you got to make sure you remember that. Otherwise, you flip them up. So really, this is saying this is true negatives and true positives. So that's good. These numbers are bigger than these. That means our algorithm is getting it right more often than not. But we already kind of got that sense from the 77% accuracy. But you can see clearly here how our algorithm has more false positives than it has false negatives, meaning that it has more errors where it's basically saying, in this is 340 days that we're looking at. Of those 340 days, 50 of those days, our algorithm said YOLO, buy it now, buy Ethereum, when it actually went down in price. And only 28 of those days did it say, hey, don't buy it because I think it's going to go down in price, and then actually went up. However, 123 days, it said don't buy it, and yeah, the price went down, so it's good you didn't buy it. And then 139 days, it said to buy it, and yes, the price did go up, so it's good that you bought it. And if you combine both of these, you can see that we have well over 250 days that our algorithm is getting the right answer. But of course, it takes just one day for us to lose a lot of money, really. Because if this is just saying it's going to go down, but like this could be like a 50 or 90% crash. We're screwed anyways. So be careful when playing with this stuff if you're actually using it for finance. But yeah, okay. So if you want to store the output of this in a individual variables to play with, you can do that. Just go again, like I said, you gotta make sure you get them in the right order. So I believe this is the right order: true negatives, false positives, false negatives, true positives, and then just store the output of the confusion matrix there. So take this code. Remember, a function in Python can return more than one value. It's just you gotta remember the order it's returning them in. And yeah, we can then print them out. Oh, I need to ravel this because it's basically remove the square brackets, make it into like individual variables, which I can just do by that. Yep, okay. So there are numbers. As you can see, we just took them out in that order, okay? And I think this is the order. Again, I have the documentation somewhere here. And let me see, confusion matrix. You can see right there, true negative, false positive, false negative, true positive confusion matrix. So yeah, and there's an example of ravel actually there. So yeah, so just make sure you don't flip these around because you will have no way of knowing from that. So yeah, just be careful. Remember this order and you're set. Oh, not remember, just write it down somewhere. Okay, so now that we have our four values for the confusion matrix, we can compute precision and recall by hand. It's just as easy as doing the formula. Let's do precision first since we did that one first. So remember the formula is just going to be true positives divided by true positives plus false positives. And yeah, that's pretty much it, right? And we said less false positives, the better precision. And we can see that we got 7354, which is exactly what is over here. So that means that this is indeed the precision. Okay, so that's good. We got the same result, so that means that we compute our precision correctly, and that is indeed the right precision. We can do the same thing with recall. That's true positives divided by true positives plus false negatives, right? Because remember, when it comes to recall, the less false negatives, the better recall. You can see that that also gives us the right value for that, 8323, right? So that's good to go. And if you want a way to just a way for you to actually remember like precision and recall, think of like a recall as like PTSD in a way. Like your model is really doesn't want to give you wrong results that are like that will get you in trouble, because it's like, it said no when it should have said yes. So like it didn't remember well. It didn't recall well. So I don't know if that's gonna, at least that's the way that I remember it. It's really weird, but it works for me. Another thing I've heard is when people say precision, it's like how good it is. and not being like, I'm not always just saying yes. Because if it always said yes, your false positives will be all over the roof, right? So how precise is it? Is how good is it not saying yes? So I don't know. I'm just trying to think of ways for you to remember it. But whatever works for you, just don't get confused. I mean, you can always Google, like go to Wikipedia. There's a Wikipedia article on precision recall and like refresh your mind. But just make sure you don't flip them, because that's one of those like rookie mistakes that makes you look bad. So yeah. Okay, let's do the harmonic mean now. So like I said, this is actually the harmonic mean, this third value here. So how do you compute that? That one is tricky. Well, it's tricky if you don't know what harmonic mean is. If you're into math and you know that, then you're good to go. But it's just I believe it's the precision times the recall divided by precision plus recall. And then I think you multiply that times 2. Okay? Now, precision and recall, what are those? Well, you gotta just algebra it, man. So just plug it in. So like, for example, if you want to do this, let me copy and paste recall. So this is recall. So recall there, recall there. You recall that. Get it? Plus, times, divide all of that, multiply everything times 2. Okay, now you can see that's a massive formula. If I just said like memorize that formula right now, you would freak, and I didn't tell you like that that's how I came up with it, you'd freak out. Particularly if you see it in like one massive line, right? But if you just remember that this is what it is, then it's a lot easier, as long as you remember what precision recall are. So yeah, that's just harmonic mean. There's no, and harmonic mean is not something you just use for precision recall. It's just like the harmonic mean is the precision and the recall. That's what that really means. So if we want to compute that, it's going to be a lot of copying and pasting to make sure I get it right. So we're going to do 2 times, and then we're going to put in the top part, which is precision times recall, and then divide all of this by, and then open parentheses, precision plus recall. Of course, you could just put these in variables to like in the line above to avoid me doing this, but whatever, we're committed now. And there we go. I think that's good to go. We'll know if we get the right answer. All right, so we got 7808, and the answer was 7808. Yeah, we did it. So now look how spooky and freaky that line looks. It's just like blah, blah. So, but yeah. But hey, that's why you scikit-learn. You just call this one line of code, and then you look at all the work it's doing in one line of code. Like just remember this line of code, and then like remember like this line of code, and that's it. But I'm trying to do them by hand because I want to make sure you understand them, right? That's why I'm manually computing them. This is for your benefit, okay? Anyways, so we understand this works. That's good. Let's move on to testing it with some like real scenarios, right? Because remember last time we tested it with two inputs, right? We tested it with like some random closing price, and then we tested it with like that 221. So let's just tweak these and test it with that and see if our model is going to just casually work with those two new days. So like, right, you got your model working, you're super happy with it, you're deploying it to the real world. It's gonna run now. It's gonna let's see if our model works in the real world. Like if we make money or we lose money this day. Okay, obviously, improve the metrics, which means like fix your algorithm, make it better before you try it. But let's just say that you're like, it's good enough. We're gonna go for it, YOLO. It's better than the coin flip, which is what I'm going by, you know, before the algorithm. So why not? Okay. So yeah. So all I gotta do, remember, is change this to logreg because I changed the name of the variable. We fit it in the same numbers, and then obviously we don't need to do the absolute value thing. Instead, in here, I'm gonna say expected value is going to be, what do I want to expect there? I don't know, let's leave it for a second. And then predicted is going to be my answer. So what is the expected value? Well, the opening price is this, and the closing price is this. So I should have a 1 to buy, right? Because I mean, the closing price is higher. So I should expect a 1. And let's see what we get from prediction. I think we got a 1 because we saw the answer earlier, but let's see. And then let's fix it here. Expected 1, predicted 1. You can see that the model works. Now we are getting a warning. User warning does not have valid features. That's because we're feeding it numbers and not a data frame. So I could convert this into a data frame, or I could convert the model into values. So I can do that quickly by just changing it here. Remember, this is what I said earlier, that I was going to probably have to go back and fix that. That's okay. It's not that the model's not working. It's just that if you're going to use the data frames on it exclusively, you don't need this values part. But if you're going to mix just throwing in numbers instead of data frames, then it'll yell at you. So just, you know, dot values to remove warning. Or the comments are, remember why I did that. So there you go. See, the warning goes away. It's still a list though. So I guess if I want this to actually show me the value, I can do that. There we go. Now it's a number. Okay, so I can just feed that to whatever API I'm using for like, you know, for Gemini or Coinbase or whatever. For the crypto, right? Which is APIs, by the way. And you all know how to use APIs now because you did the web scraping videos. Okay. So that worked. Let's see if the next one's going to work. So this is taking the data that we took the last day. So I could take data right now, but I don't really feel like it. Ironically enough, it's almost the same time. This time it's 4:30. It's actually, well, daylight savings time and whatnot. Otherwise, it would be almost the same time because it's 4:35 a.m. right now. Very cool. So yeah, we're just going to use this data and see if it'll work with that data. So that's like real world data. So the algorithm has never seen that. Remember, our model ends in like August of last year. So like, this is almost like 6 months later, and we're going to see how the algorithm is going to do. So first of all, change these names. Remember, I did that to not forget to update everything. And then we're feeding it that array of the opening price, the closing price, and the Ethereum opening price. And let's see what the model is going to predict. So our expected answer from this should be a 0, because you can see the price went down. Like, oof, yeah, it went down like almost $100. So it should be a 0. Hopefully this gets us a 0, but we'll see. So let's see. Predicted. Okay, I just remove that. And voila, there you go. So yeah, I can put this 0 again because it gives us a list back. But yeah, it gives us 0, so that's cool. So this is a true negative, right? So this was a true positive up here. That we got a 1 when we should buy, and this is a true negative. So in both cases, it's good. The algorithm understands that like it was a dark day on Bitcoin that day, and Ethereum is probably on the same page. So very good. Does that mean we're ready to go? No, because remember, we look at our metrics. Just because like we got lucky these 2 days, we're still playing with fire with these metrics. It's not anywhere close to 100%. So, but hey, at least we got lucky on those days. So that's kind of neat. Great. Okay, so the last thing I want to show you is some plots, just because it's always nice to visualize what's happening. So let's just go ahead and like just we're gonna throw all this away, so let's just dump it all. And just kind of start from there, okay? So what can we plot here? Well, it's not very exciting to plot like linear regression. Like here, let me actually, before I delete it, let me just show you what this would have looked like otherwise. Like I mean, actually, if I just run this, it's gonna, yeah, it might run. We'll see. Yeah, so it runs, but like, you can see it's just a bunch of points. If I change this from black to like red or something, this makes it easier to see. So like, yeah, sure, you can see the relationship between the opening price, the closing price. This label's wrong, it's not ETH close now. It's actually the prediction value, which is a 0 or 1. So the first thing you can see is that because it's binary classification, it's no longer like continuous, right? It's either 0 or 1. So that's why you see two complete different groups of data. You have the one on the top and the one on the bottom, right? In fact, here, before it bothers me, let me change this to decision, like the better label there. Okay, so you can see the decision is either a 0 or a 1, right? So you can see it's like, that's why the data looks like that. But you can see there's a bunch of like points on each side. So it's not really like this graph doesn't really tell us anything. I mean, yeah, no, it doesn't, like it tells us nothing useful. So that's why I'm saying, you know, we're gonna just throw this all away and kind of come up with something nicer to show. Something you can show your boss, per se. Okay? So what I think is actually useful when visualizing, like, it's a lot easier to visualize linear regression because you just draw what it's predicting and you can kind of see it that way. When it comes to classification algorithms, you saw in the other video with the iris data set, like you can draw some pretty pictures with like different classes and whatnot, and those are nice. But from a data analytics point of view, like would help you visualize, and your boss, if he's also a data analytics person, like, it's more of visualizing these values, like these metrics. Like if I can visualize these metrics, then I can better grasp what's happening. So that's what you should focus on. So let's focus on trying to visualize the 4 different types of output that we get on the confusion matrix. So the true positives, the true negatives, the false positives, and the false negatives. Let's visualize those. And also, because we don't do this too often, let's actually make a graph, like make multiple graphs in the same image, right? Because like so far, like what you just saw was one graph in the image, but like sometimes it's cool to like have multiple ones. So let's just make 4 graphs in the same image that represent the 4 cases of true positive, true negative, false positive, and false negative. Okay, so that's what I'm going to do. Now, doing that though, easier said than done. It's more about like setting up the data than it is about like actually graphing it. Graphing it is pretty easy. So let's actually set up the data first. So what I need to do is I need to actually separate. So I have 200, I know I have 240 results, right? And I know that of those, 123 are true negative, and then I forgot already. Let me see, it's true negative and true positive, right? Yeah, no, false positive. So this is true negative, false positive, false negative, and true positive. So I know that I have these. So what I need to do is I need to split them. So I need to make 4 lists, and each of them contain these separate. So how do I split them? Well, just a for loop. Just the same way we made that initial 1 and 0 list, just looping through each one and classifying them. That's what we're going to do here. So I'm just going to make a little for loop that says for I in range. And again, the length of the output, which is prediction, because remember that's what gives us a 240 result. And then just as we go through each of them, we're going to compare what it's predicting versus what we expect it to get. And that we'll know which of the groups it fits into. So actually, before we do that, we need to make the list that we're going to store the output in. So true negative, false positive, false negative, and true positive. Okay? Now we need to store, what are we going to graph? Like we can we obviously want to graph like something that shows us like useful information, right? So we know that we already separated them into their own graphs. So like all the true negatives are going to be in one graph, but like what do we put as the x and the y axis? So for the x-axis, let's just go ahead and list all the sample points. So like point 1, point 2, point 3, which represent the different dates. They're not going to be all like the same continuous calendar series, because remember we randomly picked when we separated from our test from our training data set, because that's good. We do that because otherwise we just get stuck in patterns from like, you know, what happened one month versus a different month. So like a really good month versus a really bad month will screw us up, whereas picking randomly avoids that issue. So it just makes sense to just list them out in the order they're at. Doesn't matter how they are, they're just going to list them out. So we know our x-axis is going to be just listing them. For the y-axis though, I'm going to use Bitcoin price, opening and close price. Ethereum price I could list also, but not as important, because I think really what we're trying to figure out is the Bitcoin price is connected to the Ethereum price, right? So if I can plot a point for the opening price and a point for the closing price, then I think I'm going to be able to have a useful graph. So it's good to visualize what I'm thinking about. So for example, what I want is for the true positives, I'm going to have each of these represent like sample 1, 2, 3, 4, and so on. And then this is going to be price, or just money. So I'm going to put a bunch of little X's, or I'll choose a color, and the X's are going to represent the opening price. Actually, let's do circles for opening price. And then the next for closing, because the next just seems like the word, it just makes more sense for the word close. I don't know. To me, it does. And so the closing price, you know, if it's up, it's going to be something like that. If it's a negative day, it's going to be something like that. If it's somehow the same, then it's going to look like that, and so on. So like what this will tell us visually is like if we see that all the true negatives, obviously the true positives, it means that like it's going to show only the ones where it means to buy, and you're only going to buy when the price goes up. So you really shouldn't see any of those here like that. If you do, then you know something is wrong. So that's a red flag that you can check for. But more importantly, what it's going to tell us is like some of these scenarios, we might see like really close or really big cases, right? So if we see that we're missing a lot of the close ones, and we see those in like the false positives, then we know that we're having issues whenever the price is really close in between. But when the price is like massively different between opening and close, like the day was huge gains or huge losses, and we're having an easier time with those than we are with the ones where it's tight, which would make sense. We can actually see if that's the case by visualizing the opening and closing price. So that's what I'm going to do. I think that's a good visualization that you can do that will not just be pretty eye candy to get your raise, but actually to like understand where the algorithm is struggling and where it's not, so you can make it better. Okay, so let's store that, both the opening and closing price. So I'm going to go ahead and make this a list with that's going to basically be for each of the entries we want, and within those we're going to have a sub list for the opening and a sub list for the closing price. So it's going to be like a little 2D list for each of these. Okay. Damn it, we missed the closing bracket. So again, the reason why this is a two-dimensional list is because, so I have this. It's because the first layer of the list is because I'm going to have a bunch of entries. So it's going to look like this. So I have a bunch of entries. So like entry 1, 2, and 3. So that's why I have a big list. And then each of those entries contains the open price and the close price. So it's two values, okay? So I guess I could, yeah, we'll do it this way. Makes sense in my brain, okay? So yeah, all right. So going back to our loop where we left off, let's go ahead and check. So look at compare the prediction value at this index. So like, let's say index 0, so the first row, compare what we predicted and compare what it should be. So, and then fit the 4 cases. So first case, we predicted a 1, so we predicted we should buy. And the correct scenario, I'm going to use values so that I get the right, so that I can actually access the indexers. Remember, if I just say white test like this, it's going to try to access like hatchet basically. So I just want the actual values and then just get the index of a row in that list. So what I'm saying here is, if I predicted to get up to buy and you actually should have bought, then this is a true positive, right? Because this is like, my prediction is, yes, it's going to go up. And it actually did go up. So yes, it went up, did go up, that's true positive. So if that's the case, then I want to append to the true positive list. And I want to make 2 appends, at spot 0 and at spot 1. And I want to append the price values. So the opening price I have an extra bracket in there, don't I? Yeah, I get rid of that bracket. I want to append the opening price, but I want to append the value of that opening price at this specific row. So of the column of opening price, those values, I want 5th row, for example. So that's what this line is doing. I am appending the opening price to this list, and then do the same thing, for the closing price, which is just called price, remember. Okay, so I'm just making 2 entries into that list. Again, this is so that I can graph it properly, okay? Could I graph it differently? Yeah, I could have, but that's okay. It'll make sense when we graph it, because we want to have 2 separate lists that we're graphing. One, because we're graphing essentially 2 points per entry, because one's the opening price and one's the closing price. And we're just making a list of those. Okay, so that's it. That's what we got to do for all 4 cases. So just write an else if, and then just basically change this. So let's go ahead and do the one where the prediction says to not buy, but, and then the expectation was not to buy. So like a true negative. Okay, so like the model said price is going to go down, so do not buy. And the correct scenario was that it did go down, so that's good because we didn't buy. I mean, well, it's like, yeah. It's good because we didn't buy, yeah. Sorry, my neck hurts, that's why I keep doing this. But yeah, it's a weird position. Have the keyboard over here and the camera here, and unfortunately, that's kind of what I'm dealing with. Okay. So yeah, so for those, we just append it to the true negative class or list. So you just switch those to true negative and you're good to go. See, that's why I did it like this, because it makes it easier to code it. So now we have false positive and, oh sorry, we have true positive and true negative. So now we need the 2 error class, lists. So put another else if, and in this one, let's go ahead and say that we predicted to buy, but we shouldn't have bought, right? So like we said buy, but like the price went down that day. So that's a false positive. Okay, so in that case, store the opening price and the closing price of that day into the false positive group. And finally, the last one, you don't need to put an else if because it's an else, because like if it's not one of these 3, then it has to be the last case. I'm still going to write it as a comment just so that I remember. I think, frankly, I like doing that with my else clauses in complicated code. It's just nice for me. So it will be the scenario like this, where we didn't buy, but we actually went up in price. So that's a false negative, which is no biggie for finance, big biggie for medical, right? Okay, and that one's just going to be false negative. So yeah, all this work is just to prepare the data to visualize it. Like, you got to set it up. Okay, so now we have our four lists that we need to plot. So now let's go ahead and make our plots. So we're going to make a new figure, and I believe we already imported matplotlib. Yep. So we're going to plt.figure. And so here's some nice educational matplotlib time. When you want to do a multiple, when you want to do just one graph, you do like plt, and then you just like add the plot or whatever. You can see other videos for how we've done that. But when you want to make multiple plots or subplots within a bigger plot, what you do is you just use a function called add subplot, and you store it. So I'm going to call this ax1, ax2, autocorrect is weird, ax3, and ax4, my four subplots, and I'm just going to call fig.add subplot. Okay, so I have to do that 4 times, but I do need to pass in a parameter. And this parameter is kind of weird, and I don't have any documentation map. I don't have any documentation readily available, but you can Google it later on. Basically, you pass in a number, and this number is going to represent the ordering you want to plot. Okay, if I recall correctly, the first number of this sort of combination of numbers you pass represents the number of rows you want in your plots. So we're going to do 4 plots, so we want a 2 by 2. So you would basically say 2 by 2, so 2, 2. And then this is the first of those 4 plots that you have. The second plot, here let's do a 4 and I'll come back and explain it. The second plot is going to be 2, 2, 2, 2, 2, 3, and 2, 2, 4. So the number is code to represent what you're trying to do, the way you're trying to graph it. So go to this. It's a bit easier to show. So when you say add subplot, and you can probably just Google like add subplot documentation and find this. You're passing in some integer, okay? And this integer is going to be 3 digits, usually, okay? Actually, it could be more than 3 digits, but in our case, it's going to be 3 digits. In most cases, unless you're doing, if you're doing more than 10 plots within the same subplot, then it would be actually 4 digits after that. So the first digit, I believe it's the rows. The second digit is columns, like number of them. Number of rows and number of columns, okay? And then the last one is which plot in the rows column you are adding. Okay, so let's say you wanted to make a 2 plots, just like a 1 by 2. What this would look like would be 1, 2, right? Because you have 1 row, 2 columns. So that would be this example, okay? And when you're declaring it and you're doing add subplot, you would do 1, 2, 1 and 1, 2, 2. 1, 2, 1 would be this one, and 1, 2, 2 would be that one, okay? In our scenario, because we're doing a 4, like a little 4, 2 by 2, it becomes a 2, 2, 1, 2, 2, 2, right? Because we have 2 rows, 2 columns, and then it's essentially 4 pieces. So this is 2, 2, 1, 2, 2, 2, 2, 2, 3, 2, 2, 4, I think. Okay, I think it goes horizontally. That's just the way I remember it. I don't think it goes vertically. It goes like a matrix, basically. Okay? Just out of curiosity, suppose that you wanted to do something that was like this. What would you do? Well, you have 2 rows, so the first number would be 2. You have 3 columns, so the next number would be a 3. And then this would be based on where it's at. So this would be 231, 232, 233, 234, 235, 236. Okay? So hopefully you can see why, as long as you have less than 10, this would be still a 3-digit number. I guess let's do one example where like it's 10. So let's just do a 2 by 5 or something. Okay, so you have 2 rows. So the first number is a 2. You have 1, 2, 3, 4, 5 columns. So the next number is a 5. And then here you have 251, 252, 253, 254, 255, 256, 257, 258, 259, and I think this one, I don't usually do that many, but I think this will be 2510, I think, okay? If I recall, that's the way it works. So, yeah, but you can check more documentation, okay? We're not going hardcore with like 10 things, we're just putting 4 of them. So that's where those numbers come from, okay? But you didn't think we would be learning Matplotlib today, but we are. Okay. So, yeah. Now that we've done that, let's go ahead and just make some titles before I forget what each thing contains. So we can use the set title for that. And so the first one is going to be true positives. And then let me just copy paste this. It's dangerous to copy paste, but it also saves time. So you gotta accept a certain degree of danger when you're coding. This is true negatives next. And then false positives. And then false negatives. Okay. That matches what we did up here. TP, TN, FP, FN. Yep. Okay. All right. So we got our plots. There's nothing in the plots right now. In fact, I think if I it won't error out, I think. It just will be like nothing happens. But here, let's try this APLT show, which is to show the plot. So she just shows an emptiness. There you go. So you can see the 4 plots right there. They're empty right now, but you can see that it's 4 and 1. See, that's pretty cool. Yeah, and then they're labeled and everything. If we wanted to test the that scenario with the 10, you could just add those in and test it without filling them in. So something to try at home. Try it out. Try making a bigger one, even if it's just empty for now, just to see if that 2510 thing would work. 2510 would work. If not, leave a comment below. Okay, so let's actually add the data in. So for each one, we're just going to make a scatter plot. So I'm going to add, say, AX1 scatter. And then I'm going to go ahead and add both the buy and the sell price. So I'm going to do 2 lines, one of them for the buy price, not sell, buy price and closing price. Okay, so remember the x-axis is just going to be numbers. I'm going to go ahead and just print out for now like 28 numbers, because I know it's going to be super crowded, so we can print out like all cases the same. But I think I just for the initial graph, so it looks okay, let's print out 28 of each. And I say 28, by the way, because this has 28. So obviously, if we go higher than that, this graph will have less than the other ones. But we can try printing out all of them later. But let's just start out by printing out 28 of each, and then we can change it back. Okay. So yeah, range 28, and then the next thing is going to be the opening price, which we kept there, and we're only going to print out 28, so we can use lists like that. Just print out the first 28. We actually don't need this here, but I'm going to put it in to be explicit. Last thing is pass in a color, so let's just use blue for the buy price, and then for the opening price, and then for the closing price, let's use green. And this is 1. Okay. So before we go any further, since we know the graph works, let's just try graphing one of them and see what happens. As you can see, we get one of them. We can make it bigger so it looks nicer, but yeah, it's only 28. What if we try printing out all of them? Let's try printing out all of them. If we want all of them, this would be the length of, I don't know, TP0. This could be 0 or 1, doesn't matter. And then here we can just remove this completely. Oh, well, that's only going to graph one set of them. Crap. Hold on. I got to do the same thing on the one beneath it. There we go. So that would be all of them. So see why I didn't want to graph all of them at once, because it's just too crowded. Like, it becomes harder to see it. But yeah. Now you might be noticed, like, hey, where are all the blue points? Well, I probably... No, I still kept it. Oh, but I should... So it's a 1. There we go. Now our blue points are there. So if I use the zoom symbol here, and then just like zoom in on a section, we can see that, again, the blue is the opening price and the green is the closing price. For the true positives, it's kind of expected that the green should be above it, right? Because these are all buy days. So we should see them all on top. Where is this one though? See? Oh, see, it's like really tiny. Is that going down in price? Blue is opening and green is close. That's an interesting one. So really, if I let me zoom out again. I forgot how to zoom out now. I thought it was right click. Actually, I think I can use the scroll wheel. Ah, whatever. Let's just rerun it. Or actually, I think you hold down the mouse button and then you move your. So I think if I hold down the mouse, no. No. Oh, you see, right? Yeah, so you right click and then you make a square. Which you can see I just like super zoomed out. But yeah. Okay. So yeah, so you right click to zoom out, but I overly zoomed out and broke the graph. So yeah, you're kind of expecting to see all the green ones above the blue ones because it means that like it's, you know, it went up in price. But I'm curious as to, oh, you know what it might be actually? It might be that there's a no, because each one's on its own point. That's a weird one. What could have happened that made that be the case? So what that means is that the Bitcoin price went down that day. However, the Ethereum actually went up that day. And not just that, our algorithm said to buy it and it was correct. So that's what that means. That's really weird, actually. Like, not weird because like it happens, because I mean, yes, it happens. But like, it's weird that like our algorithm actually got it right. That's interesting. Because like, it's weird. I mean, like, think about it. Like, the Bitcoin price went down this day. It went. I mean, it's very little that it went down. It looks like it went down probably under like here. If I zoom in more, so from like 47,075 to about 47,000. So like about $100. This is about $100 drop. approximately. So Bitcoin price went down. Ethereum price, however, seems like it went up that day. And we were correct to guess that it went up. So so there's something about the opening price of Ethereum that like must have flagged it. I don't know. That would be worthy of looking closer at to see why and like how that ended up happening. And for that, I think I'd have to also maybe graph closing price on my own to see and other things. So, but yeah, that's pretty cool actually. If I had more time and wanted to like look at, I would look closer at that because there's probably some interesting analysis to be done. But yeah, as you can see, that is information that I would have not otherwise have discovered. So I just discovered something interesting there and something that I could then go and look further into and maybe use that knowledge to improve the model as well. But just the discovery in general is pretty good. So there is a certain degree of an argument to be made for using graphs to learn stuff more than just using models. Like it's a tool that is not just for like showcasing your boss. You actually can learn from graphs, and I think some of you already knew this, but yeah. Okay, so anyways, let's go ahead and do the other graphs in there. So a lot of copying and pasting, but here, I still wanna like. Bother. It's really big, so like I just want to make it like a couple of points for now. So I'm gonna go back and bring this back to how I had it, with just 28 points, and I want to make it even, so I'll do it like that. So yeah. Okay. Make sure that that's running. Yep, that looks nice. Okay, so let's just copy paste is the way. 3, 3, and 4, and 4, and since actually this one is the size 28. We can actually leave the length thing here. False negative, and then true positive, or false positive. False negative, I mean. The length of the false negative. I guess to be proper, we want to put a 1 there just in case, protect ourselves from weird things happening. But yeah, we can do that for length because that one is actually 28, but the other ones are not, so we're hard coding it to 28. I just gotta make sure I update these. So the second one's true negatives, so we'll make these TNs. I'm getting that from up here, by the way. I'm not like magically guessing this. Just so that they match the label. Okay. So there you go. That's it, by the way. I mean, once you have your PLT show in there, we're in business. Look at that. That's pretty. I like this. It's eye candy. So we already looked at true positives. Let's look at true negatives. So true negatives is the other way around. We should mostly see the blues on top. But now I'm curious about if we have any other flip there. So we have the opposite. But yeah, let's zoom in on a couple of these to see. So let's look at these. So yeah, let's look at that one. Yep. As long as we zoom in, that was actually pretty close. Look at that. It's like a $20 difference and it's still got it right. Zoom out. Oh, zooming out is not. It's not nice. But yeah, the other reason why I wanted to graph this is to see if our model is good at that, actually detecting the small changes and and not just what I assume to be the big changes that are easy. And it does seem like it's doing a decent job, regardless of whether the difference is like $10, $20 or $100 or $200 out there. Seems to be doing good at that. But let's look at the error ones. The error ones are good because we can hopefully discover something. So off the bat, one thing that I see is the false positives have no like massive changes, right? Except for like this one, which I can kind of see a blue and a green. Like you can see that like some of these have like big gaps in price. It detected successfully those, but for false positives, there's no big gap in prices. So that is telling me that at least like I'm not gonna buy one day because it tells me to buy, and then the price crashes like $1,000 or a huge amount. So there's that. At least I'm not gonna lose that much. Whereas with the false negatives, there are some cases where there's like big gaps. So that does say that sometimes I'm gonna lose some big gains potentially there. But hey, I'm more concerned again about the false positives in this specific scenario. So okay, we can see that this is kind of a special one that's up here, but most of the problematic, and this makes a lot of sense actually. The fact that we have most of our errors down in this price range, well, I mean, you can see most of them, like, it does seem like in general, the price ranges are on these levels, right? The high price ranges are limited because our data set doesn't have that many, just based on time periods, because it goes from 2017 when Ethereum was a lot less money and Bitcoin was a lot less money. So you can see that like most of these, I mean, like I think Bitcoin passed 20 something thousand, like, well, at least past 30,000 recently. Before that, it didn't get there. So that's why most of our data is down here. But interestingly enough, there's no false positives except for these two when it goes over these amounts. So that tells us something already. But more so, you can see that like the really low prices, are showing up in false positives, which I kind of expected because those are smaller price differences and we haven't normalized the data or something. But let's take a look at these. So you see they're really close in price. I'm gonna have to zoom in on one of them just to see. So you can see the difference there goes from 6360 to 6400. So that's $40 difference. But what is $40 out of 6400? So let's say 40 divided by 6400. So like it's less than 1%. It's 0.06 of a percent. Wait, half a percent. 0.6 of a percent. So like it's half a percent basically that that the price fluctuated. So the algorithm will struggle with smaller changes, or at least I think it would. And it does seem to be struggling with some of those. At least compared to these where like it's more visible changes. Now, the false negatives, that one is weird. Let's see, like for example, this one. So this is like the price went down for Bitcoin from like almost $38,000 to 36. That's a big change when you think about like $2,000, but it's still a small percentage again. If you do 2,000 divided by 38,000, well, that's 5%. So it's a bigger change. It's basically not actually. Oh, well, darn! I wish I hadn't zoomed out, because was that a price increase or a price decrease? I didn't see that actually. Darn. Well, you're watching the recording, so look again, because what I'm thinking is if it's a price decrease, it's kind of what I expect. Like a false negative again tells you that like you know, it's just like don't buy but the money goes up. So like other way around. So like if it's a price increase, like then yeah, it's like okay, oh well, you didn't buy. But if it's a price decrease, that tells me that the algorithm is like trusted that Bitcoin price went down and didn't risk buying Ethereum when it went up, which would make a lot of sense. So yeah, so like I think it was this point, right? Based on the prices, I think it was, we said 38 to 36, so yeah, I think it was this point. Yeah. So green, so blue is purchase price. So yeah, so this is what I thought. So Bitcoin crashed this day a little bit, 5% crash. Well, I don't know if you call it a crash, but it went down 5%. So our algorithm got this as a false negative, meaning again that it said like, yo, I am not like, don't buy today because like the price is crashing in Bitcoin. So this probably might happen in Ethereum. And frankly, that's a pretty smart decision from the algorithm. I probably would think the same because I do think that they're correlated based on what we saw in the other video with the linear regression. So our algorithm, like, even though it's a false negative and it's a mistake, it should have bought, I can absolutely understand why it chose that. It said like, hey, Bitcoin just crashed 5%. More than likely, Ethereum is going to be negatively affected. But hey, this was one of those cases where it wasn't. Ethereum actually went up that day. Why? There's a lot of external factors we're not looking at. Remember, we're just looking at three features: opening price, closing price of Bitcoin, and then opening price of Ethereum. We're not looking at news articles. We're not looking at Twitter. We're not looking at like world news in general. We're not looking at forexes and tons of other external factors, that happen. There's a lot of things that could have made this happen, this flip. And I'm not surprised because I do recall that there have been scenarios where Bitcoin has kind of been wobbling down and Ethereum has had like tiny little bubbles or, like exciting periods where we're not. This was probably one of them. So I can understand why. And remember, the algorithm is only looking at current day. That's another thing. You want to make the algorithm wiser, you should make it look at not just current day data, but look at other days' data and combine it. That's a cool thing to do, actually, to do that. But it will take longer time to train because you're feeding it input from, like, let's say you're feeding it from not just one day, but like previous 2 days. How would you do that? Very easily. Just add more features. Instead of just adding in the buy and the closing price, opening and closing price of that day, also add in the opening and closing prices of the previous day and the one before. So now your algorithm is actually looking at historical data to make a decision rather than just present day data. You got to tweak around now, like things like the training and test split, because you want to actually have chunks of data that are like in trios. But you could very well do that, and you probably have a little bit of better performance because the algorithm starts to see trends. Like, hey, if it's going down the past 2 days, it's probably going to keep going down unless it like randomly U-turns, right? So, but yeah, interesting piece of data that I just got from the graphs with the false negative. I understand this one. I understand why, and I also understand that there's really no way that I could fix this error without additional features because Bitcoin's going down in price. The algorithm's like, hey, it's crashing. I mean, like, did you really want to risk it? And so that's it. So interesting. So there you go. I could look at this and spend longer on this, but this video is getting pretty long. So I'm going to go ahead and stop there when it comes to the visualization. You can make your own conclusions and drop them in the comments later if you want. But yeah, so let's kind of summarize what we did. We started out with the same example from last time with the linear regression. We went ahead and we added a brand new column, which was a 1 or a 0 based on whether the price of Ethereum went up or down that day, comparing the opening and the closing price. Once we created that sort of extra column, we go ahead and made that our Y value. So right here, we went in and loaded our logistic regression. We used this solver. Like I said, go ahead and try other solvers on your own. Maybe you'll get better results or not. Let's really quickly just do one. Let's do one other solver. Let me open up the linear regression. Scikit-learn. So is this linear regression? Yes. Okay. Solver. Oh, this is linear. No, logistic. Why is this linear? Here we go. So let's try our faster. Let's try live linear. Why not? One versus rest. Yeah. Why not? It's whatever. I think the one we have now is probably the better one, but who knows? Live linear. So remember these values. So we got 73, 83, 78. Yep, we pretty much got about the same. I'd have to like copy and paste them to remember them. So let me copy them into like a notepad file or something. Okay. So now let's undo that change and rerun it. They are identical. Okay. I guess it's just defaulting to that. Let's try Saga. There we go. We got something different with Saga. So with Saga, we got a lower precision. So we got a 68% instead of a 73%. But we got a really high recall. Look at that. Our recall went, well, not really high, but it's a lot higher than before we had 83%. Then we got 89%. So it appears that this solver is essentially improving it's decreasing the number of false negatives that we have. So before we had, I think, 23, and now we have 18, right? So we have a couple of less false negatives. Now, it could also be just a random state. It's possible. But I think it's statistically significant now, difference. So unfortunately, though, remember, we actually care more about precision in this scenario, right? Because we don't want that many false positives. And here we definitely lost precision. So whereas this solver would have been nicer for like the medical one, for us it's actually counterproductive. So the other one was actually better. But you can definitely see that thing I was talking about where like precision goes up and recall goes down and vice versa, that inverse relationship. It's not always the case, but very often it's the case that there's that inverse. When you're playing around with things like models and even things just like solver. Okay, so you can see it went back, so yeah, 28. So yeah, not 23, so it's almost 10 other errors. So yeah. Should I show the graphs, how they look full? Make them all like that. Yeah, I'm curious. I want to see it. So let's do that. I should not have done that commenting like that. Shame. Right. So let's just I gotta uncomment them all. Let's just switch these. Okay, TP. Again, it doesn't matter. 0 and 1 should be the same length, but I like to play it safe. TN 1, and then these are FP. FP. And then just get rid of this. Hopefully I didn't make a typo somewhere in this. Let's see what the graphs look like now. Okay. So, yeah. Look at that. Obviously you can see that the true positive and true negative have more data points because we got more things right than we got wrong. So there's that. So yeah, so you can see false positive seems to be mostly residing on this area. False negative seems to be like a nicely even spread out. Well, slightly heavier here because again the data set. But yeah, that's pretty cool. All right, so like I said, when I was going over it, so after we created that ones and zero list, we went ahead and we used the logistic regression model. You can see the very simple change. We tried the solver, there's some arguments there. We ran it with the training data. We ran the test data set to see how it did. And then we showed the accuracy. Then I went ahead and showed you how to do precision recall, the confusion matrix values. We computed those, harmonic mean. And then we tested some values like real world examples if we deployed it. I welcome you to try it out on the latest crypto data and see how it does. And then finally, I showed you some awesome matplotlib stuff on how to make a plot that has tiny little plots in it, like plot inception, as you saw, using the add subplot function that you see right here. Of course, we had to prepare the data by splitting it into the 4 categories for each plot. And then, yeah, we just went ahead and did that. I kind of went over why these numbers exist and all that fanciness. And then, yeah, I initially plotted only 28 on each because I wanted to kind of see it the same, but then I just threw everything together. So yeah, you have both scenarios here so you can see it. PLT shows it. And yeah, that is it. So pretty thorough example, if I may say so myself. But ultimately, you got to see a nice beefy example of classification using machine learning. And so previous video you saw the iris data set, and previous video you saw this crypto stuff but with linear regression. Camera's getting blurry. But now you at least got to see like a nice logistic regression example with the crypto data set that you're familiar with. And so you can now take this knowledge and apply it to your own classification problems. Focus, my camera friend here. Please focus on me. What are you even focused on? I got a 4K camera to see if it would improve quality. And I guess it improved quality, but it also made things blurry. So I apologize for that. I'll try to see if I can fix it to infinite focus or something. So. Oh, there we go. Yay, it's back focused. Okay, stay camera, stay. Be good camera. Okay, good camera. All right. So yeah. Okay. So in the future video, I will probably revisit the crypto problem and then try out a couple of other algorithms like support vector machines and maybe other things. We'll see. We'll see what happens. But if not, like I said, it's very easy to try other models for whether it be regression type of problem or classification type of problem. Literally, all you gotta do is change one line of code, which is literally like this one. Change it to the model you want, and you're all set to go. That's what I love about this stuff. You got so much power now. You can do all the machine learning you want. Obviously, this class is just kind of giving you the tools. If you to truly understand some, like a support vector machine versus like a decision tree versus like a random forest, you have to take a math machine learning. So like math classes to understand stuff, and then to like understand the machine learning and whatnot. So like, you're only getting, it's like you're learning how to use a tool, but you're not learning how the tool actually works. And if you really want to optimize it, you have to know how the tool works. So there's a certain degree that you have to accept that you're not going to be able to do because you don't know like the hardcore stuff. But like, don't let that stop you. You can do so much just with what you already learned. So go out there and do it, and show us computer scientists that you don't need to be an expert in computer science or math to use machine learning. So I think that's really the goal, to bring the knowledge to the people, right? That's another reason why I'm putting this on YouTube, so others can watch it, right? I don't want to feel like you're limited. You have to have a PhD in computer science to be able to do machine learning or something, or just a bachelor's in computer science. You don't need any of that. You can do machine learning on your own with something very basic. And it's just some Python and scikit-learn. So, yep, that's it. Thank you for watching. I guess I'll leave a disclaimer saying that none of this video is financial advice. Please don't try this with real money, because it's gonna get you're gonna lose money, particularly if you're watching this level of video to learn. So while it's very fun to do the crypto example, you know, don't actually try to hook this up to an exchange and then go yell at me when you lost all your funds because your algorithm gave you the wrong result. So there's a disclaimer, okay? This is not financial advice, and I'm not a lawyer. This is not legal advice, and this is not medical advice. Since I said some stuff about the testing, false positives, false negatives, it's not any kind of advice other than strictly for educational or entertainment reasons, okay? Yes. Okay. I'll see you on the next video. Thanks for watching, and take care.